Yeah.
Two.
And then like
There's more than just going 1, 2, 3, 4, 5.
slightly. If only. You always depend on me.
No. That's the exact sound you made.
So you won't accept just saying, yeah, that would work like that because it, you know.
Just because? Just because you felt like it?
No, people look at it and say, yeah, that would be fucking equals.
Because I felt like it.
Right.
No, I can't accept that.
No.
Actually, I could accept it, but I won't. We'll say that. There's a difference between can't and won't.
Not waking up when.
No, that's not even, that's just me not saying.
How good are you at physics? That good.
You know, invariably, every semester, somebody asks me that question.
I only asked because I was just talking to Dr. Cooper.
Wait, what was the question?
And,
How good am I at physics?
Uh,
Invariably. You know, I think the question is how bad is somebody at physics? Because no matter what, you're going to be bad at it. You're going to fail no matter what. It's just to what degree do you fail?
It's how much you understand.
Oh, I'm only slightly bad at it. That's actually pretty good.
all I know is I've not met anybody teaching that understands physics as well. Now, I've met people that I work with that probably understand physics better than him, but I can't even understand them in, you know, regular, everyday conversation. They are disjointed.
Yeah, physics animal is a different breed. We'll say that.
Yeah, you guys ever taken a class on
Cooper?
Yeah.
I hear
I didn't, I just,
I have not to take physics here.
Just
so I'm
dropped
not going to.
yesterday.
Yeah, that's what I was.
Winner.
He's hard.
yeah.
John, that's my drinking
He'll teach you.
game.
What?
That's my
No,
drinking
but
game.
you also have to do
I
the
just
work
dropped
and
that
understand it to do well in class.
I got
Are you
computer
doing
science.
first physics class to do a three?
That's
all
all
I
I've
tried.
And then I came
What was your-
to majors, so I
Oh.
didn't need to take the other one.
Oh, okay. I think I've said it.
Drop my
I
dead
needed
glasses.
I needed the first one. Which I got.
Nobody's dropped the screen.
Nobody's what?
I like
Nobody
this
said
one.
nobody's dropped the screen. I need to be harder on that.
I don't think so.
No. Math's supposed to be fun.
It is supposed to be fun.
It's supposed. Everything's supposed to be fun. Learning's supposed to be
And
fun.
for the most part.
Yeah.
Living is not supposed to be like existential crisis.
The government's supposed to protect us. Now we can all really laugh. No.
No real.
And you work for Greg, he's coming
Ah.
late. Not this Greg. Okay.
Got it. Well, I figured that.
I'm
was
ready.
since he-
You can get through this, I think.
It's weird. It's not here. I can't hit him with anything. It's like I'm missing a part where it's good.
Maybe he's just running late.
No, I wish that'd be cool.
Scare him off.
I wish. Poor Don, in true story, I wouldn't talk badly behind his back. Yeah.
Where is Donnie?
Donnie took me for Calc 2 8 years ago. There he is. Donnie, how long? No, seriously, we were just talking about you. How long ago did you take me for Calc 2? Was it 8 years? Like seriously?
Nah, it was,
It feels like
14.
it feels like it's been a long, long time. Like,
Cause
seriously.
it was, my wife went to the nursing program 2 years, or 2 years ago, maybe, yeah, so 3 years ago.
But that was for scientific and computation, wasn't it?
Oh, wait, yeah, that's right.
Because you took me for Calc 2 way before that. And then you appeared again out of nowhere. And then once again you appear out of nowhere. I thought I was done with you. It's like I finally discovered Valtrex and my herpes was on or something like that. Not comparing you to herpes.
Just the experience of
Maybe
herpes you
about-
got compared
Then
to.
maybe 4 or 5 years, yeah.
Well, that was for scientific and computation, because we haven't offered that class in literally 4 or 5 years. So, go find one of your old tests. You know, the ones with the
I
big.
have I still have my binders.
Okay, yeah, go ahead. I'm actually interested to see, but I think it's like been 7 or 8 years. Yeah.
At least I'm still trying.
That is true. I will say that about you. You're still trying to fail. He actually passed all my classes. I don't know how, but he did. You are. Okay, guys. So I think we have to go through and do one more of my big problems involving the set stuff. And this one, unfortunately, is going to be much more difficult than the other two we looked at on Monday. And then we're going to take a look at counting methods. And when we say counting methods, it has to do with more like probability and being able to do those sorts of things. Okay? And then just a reminder, guys, that assignment number 8, so assignment number 8, that's going to be due on, what did we say, Monday, correct? And even more specifically, Monday, October 31st. So not any month, and we'll say 2016, so that way you don't get to select which October 31st you
Is
get to
it
select.
AD or BC?
We will go with AD since it might be physically impossible for you to submit it that long ago. Okay.
Hey,
All right. Any questions, guys, I can answer? Okay, so let's go ahead and try this animal right here. So we want to prove this, and this is actually a fairly common proof that a lot of times you see in with set laws. So difference of sets A and B minus difference of sets B and C is always equal to A minus B. Okay, now this is true, okay, so I'm not going to give you guys ones that aren't true. So let's go back to Monday. And remember I gave you guys that sheet with all the different laws on it? That might be appropriate to help us out. So if I was to ask you guys which law to begin with, guys, which is the most obvious law to begin with?
Set difference.
Set difference, right, guys? So you got to start with set difference. So let's do that first. Good. So this is going to be A intersect B complement, intersect B intersect C complement, complement. Okay, so everybody see what I did there, guys? There was the minus that was in the middle of the first parentheses. Then this minus became an intersection complement as a
okay.
result of the second set difference. And then inside we have a set difference there.
But that should the, oh yeah, I got it.
Okay? All right. And that's going to be equal to A minus B. And that's just our set difference. Okay. By the way, this is on the last page of the packet we looked at on Monday. Okay, so just remind you guys, this is the new packet. Okay? All right. Now, this looks very tempting to use the associative law on it, doesn't it, guys? Because there's a whole bunch of the same symbol. Unfortunately, we can't use set difference because of this complement right here. I'm sorry, we can't use associative property. So does anybody think they might have a
De Morgan?
suggestion? Yeah, I think what we would have to utilize at this point is the De Morgan's law. Okay, so let's use De Morgan's law. So we're going to say the first set stays the same, A intersect B complement, intersect. Can somebody tell me what's going to go inside that second parentheses once we utilize the De Morgan's law?
Is sorry, B is complement, then the was union,
Union.
C complement,
C.
complement, yeah.
Complement, complement. Nice. Okay, so C complement, complement. Because remember, you have to apply the complement to both of the sets inside and then flip over the intersection. Okay, that's going to be equal to A minus B. And that's our De Morgan's. Okay, nice. I think everybody knows what the next step's going to be, and then they want to quit on this one. Okay, so what's the next step that looks so obvious it hurts?
Double complement.
Double complement law, right? We have complement, complement. In fact, if you wanted to, you could skip that one. Okay, you could just go right to complement, and I'm okay with that. Okay. So this is going to be A intersect B complement, intersect B complement union C equals A minus B. Okay, so that's our double complement.
Now, do you write A? Can you do the quote A minus B on the right all the time?
What do you mean? Oh yeah, you can just use the double quotes on that. That's
Okay.
fine. I figure it's just literally 2 lines
Okay.
or 2 characters, so I'm not going to.
No, but I'm lazy, so I.
That's okay, you can do that, you're efficient. All right, now this is where a lot of students look at this and they're like, you know what, I just quit on this one, okay? We'd like to be able to use like maybe some sort of absorption law, I think, on this one to make it really easy, okay? So one of the things that students might try to do, and I don't want you guys trying to do this, is they want to take this and distribute to both of those, okay? And unfortunately, I don't necessarily know if that's going to be the best way to go about it. Not saying it's not wrong, okay? But, I don't know. We'd like to be able to use absorption if we could, but unfortunately, this isn't exactly the same as what's in here. Okay, so I think, unfortunately, the only way to try to do this next step is to actually use the distributive law and distribute quantity to intersect B complement to both B complement or C or union C. Okay, we don't want to do that if we don't have to, but I think in this instance we kind of have to, unless somebody else sees another law that we can use. But
Could you possibly use the associative to just move the brackets over to contain like that whole second expression? as one
we
thing?
could, John, if this was an intersection. Unfortunately, because there's different, because these are both intersections and this is a union, we can't move those around, okay? It only works if they're the exact same. I see what you mean, what you're trying to do. The only thing you could possibly, and you couldn't even group these two again, unfortunately. So, yeah, I think we're stuck with this one. So, and I think there's one on your guys' homework, the last one, where you're going to have to use this technique. So I want to make sure that you guys are okay distributing this to both. Okay, so if I were to distribute this, okay, the way this would look is I'm going to have one bracket, okay, because I'm going to put A intersect B complement, and then intersect B complement. Okay. And then union bracket A intersect B complement, and then intersect C. All right, so that's supposed to be equal to A minus B, which it will be. So that's our distributive property. So I want you guys to take a look at that and make sure you understand how I distributed those, okay? And like I said, there's going to be one on the homework where you guys are going to have to do this, okay, unless you don't want to get it right, okay? But hopefully this isn't too difficult to understand. But does that make sense? Any questions about the distribution there? Okay. Now, I think at this point we might be able to use that associative law. Can't we, guys? Because if you notice inside the brackets, we have all intersections. That's okay to do. I'm not going to mess with this guy over here, and I'll show you guys why in a moment. Okay, so all I'm going to do is I'm just going to move the parentheses over for this guy right here. Okay, so this is going to work out to be bracket A intersect quantity B complement intersect B complement. That's just an associative law. Okay, that's completely okay with everybody. I know you guys know associative law. The second guy, I'm going to leave him exactly as is, okay, because we're going to hope something good happens. Union A intersect B complement intersect C. If that C wasn't there, our lives would be great, okay, but we have to somehow get rid of that C. Okay, we don't have too many laws that allow us just to eliminate one of the variables or one of the sets in this case. Okay? That's just an associative law. And I bet you most of you guys see what the next set is if you're focusing on that first bracket set. So, does anybody think they might know what's going to happen next with this animal? Yeah. Guys, take a look at B complement and B complement. Guys, if you have A and A, it's equal to A. So, and Greg, that was what idempotent, so? Okay, so B complement and B complement is just B complement. Okay, so let me go over the other board. By the way, we're literally about 2 steps from being done with this. Okay, so this is going to work out to be bracket. Well, actually, we don't even need the bracket anymore. This is going to be A intersect B complement. Okay, we could put the bracket there if we wanted to, but in reality, we've only got A intersect B complement going on now. The other one is going to stay the same. Okay, so this is going to be union bracket A intersect B complement intersect C equals A minus B. So that's our idempotent law. So, suggestion at this point, maybe. No? Absorption, okay. Greg, what do you see up there? Do you see 2 sets that are completely identical?
Yes.
So, if you were to look at this set as what, like maybe A, and this set as A, and this C is the B, well guys, that's an absorption law, okay? Let's take a look off to the side. Absorption says that A union, it doesn't say anything.
Check that out.
The whole building.
Alright, it's going back.
Oh, nice. It's getting worse. Oh, there we go.
Movie time.
Put a sign for somebody laying on paper.
What's that?
Sign for a sign for somebody laying on paper.
Anyway, it's too easy. I'm not going to do it. All right. Guys, don't we see on our sheets there, if we have A union A intersect B, that's equal to A, where A is a unique set and B is a unique set. Think of this as set A, and think of C as set B. Doesn't it look like it follows the pattern of A union A intersect B, right guys? So what does that turn into if I go ahead and use the absorption law in that? A intersect B, right guys? So this is just going to turn into A intersect B complement equals A minus B. Okay. So does everybody see that, guys? The absorption law, that's going to take care of that. Okay. You have to think of the parentheses as singular A. Okay. So that's just its own set. Okay. And that's going to be by, what did we say? Absorption.
Absorption.
Okay. Yeah. Then we're done, right? Yeah, we're literally done because, what do we just have a set difference here? Yeah, A minus B equals A minus B. So that's our set difference. Okay. So, unfortunately, this was one of those types of problems where we had to utilize a distributive property on a quantity. Okay, we don't like doing that, but unfortunately in this instance we have to. Okay, and I think number 9 on your homework, you might have to do that as well. Try to model number 9 after what we did here to try to assist you with that. Okay? Alright, so any questions? Go ahead.
So this is a pretty good test question.
You know, I wouldn't put something maybe of this high caliber question on the test, because what I try to do is on the exams, I try to give you guys like middle level problems. I
So,
don't try
but
to...
it would utilize a double complement though, right? Most likely, is that what you're saying?
Oh, I mean, double complement, I mean, that's a really, really easy one. But I wouldn't say, like, I wouldn't make it so that on the exam you guys can have to distribute a quantity. Okay?
Oh,
So, but, I mean, double complement.
that's
for
what
sure.
I meant, that's what I meant. Is-
Oh, I see, yeah.
Yeah.
Okay. Yeah, I mean, I think that might be more difficult than necessary to test intermediate level knowledge. Okay. All right, other questions I can answer for you guys about anything before we move on?
It's not working, but 2011, summer.
Oh, was it? Okay. So, wow, jeez. That was what, like 6 years ago?
But I've taken other courses in between of them.
That's how you got so smart. Okay. All right, other questions, guys, I can answer before we go ahead? Okay, so the next thing we're going to take a look at is we're going to take a look at counting methods, okay? So hopefully this is going to be a little bit of a reprieve from what we've done because there's no proofs in what we're doing with counting methods. Okay, most students do very, very well with the counting method stuff. So let's go ahead and knock some of that out. Now, unfortunately, due to our power losses, I have to reboot the computer. bring back up the thing so I can see what I'm doing here, so bear with me for one moment.
If you have an extra copy, you can just use the paper and just.
Yeah, but I like being able to like demonstrate using the board so that way everybody knows where I am exactly. So, sorry, I'm one of those teachers that likes to use pedagogical implements and stuff like that. So, plus my obsessive compulsive disorder doesn't like it either. So, we'll go with that. It's more selfish than anything.
Oh, we did this in statistics, this kind of stuff.
Yeah, some of it is statistical.
Yeah.
Okay, I mean it's not high-level statistics. It's not inferential. It's all descriptive.
Yeah.
But I mean, some of the same things you guys might have seen in some of your stat classes.
Informational alpha level, right? 0.05, 0.03.
Yeah, that's more of an inference.
Oh, those are interesting, very interesting.
Yeah, when you use a hypothesis test, all that fun stuff. Oh, you said statistics, and I clicked on my statistics class. It's the,
Ho and high, right?
my bad. Okay, I'm going. Da, 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 da. Counting methods, yay. Your download will begin shortly. Shortly as in what? Yeah. I mean, 10 minutes compared to the length of time the world's been in existence is a short amount of time, so. I guess they're not lying. Oh, go away.
You killed it.
I killed it. It's killing me. There we go. Okay. So, when we talk about counting methods, I think one of the most fundamental things we can do is we can create something called a decision tree, because basically born of every sort of outcome is a decision tree. Okay? We could do this for any problem that we're going to look at in this class. However, they're very painful, which is what we're going to see. Okay? So, let's say for some reason I have a scenario where I have a red, blue, and a green marble that's placed in a bag, and I choose 3 of them at random for placement. Okay? So, and I just go ahead and reach in there and grab it. So let's say for a decision tree, I have draw number 1. Okay, I'll just label this as D sub 1. The 3 possible outcomes that could occur, so this is our decision tree, would be that I could draw a red marble, I could draw a blue marble, or I could draw a green marble. Now, contingent upon what happens on draw 1, that's what's going to happen, then a different event might happen on draw 2. So, let's say for some reason I picked a red marble in the first draw. Then I put the marble back in the bag, and what are the possible outcomes that could happen on the second draw?
Same thing.
Same exact thing, right guys? So, for the second draw, we could draw either red, blue, or green. Okay? Same thing if I picked the blue marble, right guys? So this would be red, blue, or green. Same thing if I have to draw the green marble. So red, blue. All right. So this could be potentially draw 2. So I'll label this D sub 2. Okay. And any one of those could occur because it's a completely random event. Okay. And when we say random, it means that humans can't influence the outcome of that. Okay. Most of the time when we study probability and statistics, we talk about random events, okay? We're not necessarily worried about conditional events, okay? It's just because those are unpredictable for us to be able to try to formulate anything for, okay? On draw number 3, what could happen if I drew 2 red marbles? Same thing, right guys? So I could draw red, blue, green. And then guess what we need to do a whole bunch more times? The exact same thing.
Can we just do like a double quotations?
No, sir. Unfortunately, efficiency won't work in this instance. Red, blue, green. Yeah, and then unfortunately, this is what your decision tree is. Okay, so green. Good thing I didn't make it 5 draws, right? Then you guys would just get that one wrong because you just didn't feel like doing it. Although not saying you feel like doing this one. Only 2 more. And then finally, all right. So that's our decision tree. Okay, so I'll give you guys a minute because I know you know how to do it. It's just getting there, sitting there and doing it. But basically, what you guys would do is you would just trace it to list out all the possible outcomes, okay? So for instance, one possible outcome from the decision tree is that I draw 1 red, 2 red, 3 reds. So one outcome would be red, red, red. One outcome would be red, red, blue. One outcome would be red, red, green. Okay.
Oh, you're doing permutations?
What's that?
Permutations?
They are permutations, right? Because the order, well, they're actually, believe it or not, they're actually more combinations, because the order really doesn't matter, okay? Because you can't really decipher one red marble from the next red marble. It doesn't really matter, unless for some reason you're worried about what order you get them in. Okay? All right, and then you guys can do the same thing, okay, all the way down. Okay. But guys, that's all a decision tree is, okay? And like we said, everything that we do in this class regarding counting methods could go back to a decision tree, okay? So if for some reason, like if you guys are in another class and you're ever confused about a problem, just go back to the decision tree, okay? It's the easiest way to do it, okay? It might not be the most efficient way, but at least you guys can formulate an answer, okay? So does that make sense as to what a decision tree is, guys? For those of you guys that are computer science majors, trees are probably one of the most useful data structures that you guys could use, okay? So you guys could probably see where this would lend itself, especially to a binary operator such as a computer, to where you only have one of 2 things that could happen. You could either take the red or not take the red.
Can I ask you a question?
Yeah.
Why did you choose 3 trees? Because there were 3 marbles? Is that how?
Yeah, exactly. Just because, well, there were 3 possible outcomes.
Uh-huh.
And then it said to pick 3 different, and 3 of them are chosen at random. So basically you do 3 selections, okay?
Gotcha.
So if I said that there was only a red and blue, then there would only be 2 stems, but there would still be 3 levels, okay? So this would be like a parent and then some other child nodes, if you would. Okay, does that make sense, Lauren?
Mm-hmm.
Okay. Other questions, guys? Okay. So let me show you guys an example as to why this thing would ever be useful, okay? So another question I have here, and this can relate itself to probability a little bit. 3 people have been exposed to an illness with a 50-50 chance of becoming ill, okay? First of all, we want to list all the outcomes if all 3 people are examined, okay? So what are the possible outcomes that could occur from this, guys? Like if a person's looked at,
He's either
ill or well, right? Either sick or not sick, okay? So let's say we run into the first person, okay? So we examine person 1. And person 1 is either, I'll just say ill or well. Okay? Just to make it easier, right guys? I don't want to use 2 letters that look the same and I and W look pretty different. Then based upon the first person's illness or wellness, we can say, well, person 2 is going to be either ill or well. Ill or well. And then we can do the exact same thing one more time. Okay, so, now this is one, because the next questions deal with probability, this is one where I probably want to list out all the possible outcomes that could occur. The other one I didn't list them out because, you know, I don't want to sit there and list out 27 outcomes, but this one only has 8, okay, so it's not that big of a deal. So one possible outcome is if I examine all 3 people happen to be ill. So ill, ill, ill. Another possible outcome is that the first 2 people are ill, but this 3rd person is well. And then I would have ill, well, ill. I-W-W. And then W-I-I. So see what I'm doing, guys? I'm just tracing the tree. And then W-I-W. And then W-W-I. I just thought about that.
Then
And then W-W-W. I also saw we up here, W-I-I.
World Wide Web.
And then World Wide Web. It's really neat how many different permutations and how many different words or acronyms that we can actually get out of W's and I's.
I didn't know we were one of this.
Yeah.
It's a history class.
Oh,
That's how
no,
you
no.
guess how we're all rolling.
No thanks. We stay away from history.
Yeah.
So, does that make sense, guys? Nice and easy, right? Okay. Now, the second part of the question says, what is the probability that only one person is ill? Okay, so we look through the list, okay, and what we want to do is we want to figure out how many outcomes only have one person that's ill. Well, I take a look at it, and I have one outcome here that's favorable, I have one outcome here that's favorable, and I have one outcome here that's favorable. So those are the number of ways that I could select getting one person that's ill. How many total possible outcomes are there? 8.
8.
So what would the probability be for that?
3, 8.
3 out of 8, right guys? So there's a 3 in 8 chance, okay, that if I line up 3 people and they have a 50-50 chance of it being exposed to a virus and contracting it, then that they would actually have one of those would have the virus, okay? 3 out of 8 is 0.375 or 37.5%, I believe. Okay, you guys can check that in your calculator. So it's not highly likely, but it's not highly unlikely either, right guys? So it is possible that at least one person, or I'm sorry, it's likely that one person could be exposed to the virus, okay? What's the probability that no people are ill, okay? So guys, what would that be?
That's 1 out of 8.
Yeah, that'd be 1 out of 8, wouldn't it guys? Because there's only one way that all three people would be well, or no people are ill. So this is where maybe 0 people would be ill. Okay, so that would be 1 out of 8, or that's 12.5%. Okay, so it's not very likely that if there's a 50-50 shot of 3 people trying to contract, or not trying to, but being exposed to a virus, that nobody's going to get exposed to it. Okay, it's highly unlikely. Okay, and then the last one we have, what's the probability that either 2 or 3 people would be ill?
4 out of
Okay,
8.
that would be 4 out of 8, right guys? So there's 3, 2, 2, 2. That's 4 out of 8. So there's a 50-50 shot that either 2 or 3 people.
Actually, if you add the 37.5 and 12.5, you don't need to do the other one.
Well, right, but and then we would have to take the complement of that
Yeah.
to be able to work it, okay, which we'll have to talk about a little bit later. Okay? All right, so guys, do we see what decision trees are useful for? Okay, and again, it's not one of those things that's difficult, but again, it's fundamental, okay? It's basically the building block of probability, if you would, in counting methods, okay? So any questions about that, guys? We wish the whole exam was counting methods, right? Not proof by mathematical induction, which we're not going to look at on the next exam. Okay, one of the most useful rules is the multiplication rule, okay? Multiplication rule says that if n is the number of outcomes for an event A, and then we also have that n is the number of outcomes for event B, then the total number of outcomes for A and B is m times n. In fact, we could have seen that earlier when we had the example with the marbles, right? Because we had 3 marbles, right? And we were selecting 3 of those. So we would have 3 times 3, which would give us 9 outcomes from the second draw, and then times 3 more, which would be 27 outcomes, okay? So I just wanted to show you guys that the multiplication rule is actually relatable to what we were already doing. Like for instance, okay, for the sick and well, there are 2 outcomes, right? It's either sick or well, or ill or well. 2 times 2 gives us 4, times 2 more gives us 8, right guys? So we can still use the multiplication principle to see the number of outcomes. Now what's the problem with the multiplication principle? It doesn't show us exactly what those outcomes look like, right guys? So there's drawbacks to it. It tells us how many, but it doesn't tell us what the outcomes
So
look
the outcome will have to be exponent then. And the,
It could be exponential if it's binary, okay?
Okay.
But it doesn't necessarily mean that all are going to be binary, okay? So I don't want you thinking that it's always exponential, okay? All right, other questions, guys? All right, let's take a look at some examples where the multiplication rule could be utilized. Okay? So, we have an alarm code. It can be chosen from any of the 26 letters of the English alphabet, okay? How many 3-character codes could be created if repetition is allowed, okay? So here's the way I think about these guys. I just make 3 spaces. You have an alarm code, so you put 3 spaces in. Okay? There's 26 letters in the alphabet, okay? So how many letters could we select for the first entry? 26. How about for the second? 26, and the third one? So this is one where we could just use 26 to the third, because we're not taking away anything each time, okay? So this is an example where we could use an exponential relationship. Okay? And all we do is we just multiply those together. There's 26 ways to pick event A, 26 ways for event B, 26 ways for event C. Okay? So can somebody tell me if I was to multiply that out, what that would work out to be, please?
17,576.
Thank you, ma'am. Okay. So, there's a pretty good number of these that could occur. Okay. What if for some reason repetition was not allowed? Okay, that's only going to slightly alter the number. Okay, so what would that, or what would we multiply together if repetition was not allowed?
26 times 25 times 24.
Yeah, we just take one of the letters away each time, right? So for the first one, there's 26. For the second possibility, there's only 25, because you've already picked a letter, no repetition allowed. For the third one, we picked 2 letters, so there's only 24. Okay? This is only going to slightly alter it. I think there might be about 2,000 less. You don't get it?
15,600.
What does it mean repetition is not allowed?
Once you pick a letter, then you can't reuse that letter, John.
Oh, the let. Oh, so
Right.
it's not, it doesn't just mean the code. It
Right.
means any.
Repetition of the letters. Okay. So sorry about that. So maybe I should have been more specific about that. So, but you can repeat the letters that we're using, just not the, or you could repeat the code. But if you pick, if there's only one code that's going to outcome no matter what. Okay. So there's just a one-to-one relationship between what you pick and the output for that. Okay. We're figuring out how many codes there are. We can't reuse a code anyway. Okay. Does that make sense, sir? Okay. So, by the way, how many codes did we get out of this?
15,600.
600? Okay. Thank you. So about 2,000 less codes if we just don't allow repetition. Okay. What if for some reason we allow repetition of the letters but no vowels are allowed? Okay.
20,
So,
21 times 21 times.
yeah, there's 21, 21, 21, because there's 5 vowels, right? A, E, I, O, U.
Sometimes why?
We're just picking the ones that we absolutely know are always vowels, okay? So that would be 21 times 21 times 21. Okay. It's okay. No big deal. And then what would that work out to be? Anybody figure that out?
9,261.
9261 mark.
Yeah.
Thank you, man. And then finally for the last one, if repetition is not allowed, what would that work out to be, guys?
My math is correct, it should be 7,980.
And Greg, how did you do that, sir? What 3 numbers did you multiply?
I multiplied 21, 20, and
Sounds good. And then 7,000, what was it?
9,980, yeah.
90. Yeah.
900.
7,980.
There we go. All right. So these are pretty easy, right, guys? That's what a counting method is. And counting, bless you. Counting methods are useful because remember, that's how computers figure things out. They just go one event in order. Okay. So if there's a certain number of outcomes, a computer can figure out how many different ways there are to be able to do that. Okay. We could do the same sort of thing with the Maryland license plate. Okay. So in Maryland, at least it used to be. Now I think they ran out of license plates, so they now do something different. But it used to be that the plates consisted of 3 letters followed by 3 numbers. And we want to know how many unique or different license plates can be created if repetition is allowed, repetition is not allowed. First letter is a vowel, and the last number is a 0. And the first letter is a vowel, the third is a consonant, and the first number must be 1. Okay, so these aren't too difficult. Let's just go ahead and keep these going. So a license plate has 3 letters, 3 numbers. Okay, so we're going to have 6 spaces. Now we already know that there's 26 letters in the alphabet, and it says that repetition is allowed. So for the first 3, it's going to be 26, 26, 26, right guys?
Mm-hmm.
What about for the last 3? Because they're all going to be digits.
Well, it has to be
10, 10, 10.
10, 10, 10, right guys? Because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have to make sure that 0 is included as a digit. So it would be 10, 10. Does that make sense to everybody, guys, as to why it's not 999? It has to be all 10 of the digits. And then if we multiply those out, we just basically tack 3 zeros onto the 17,056 or 76, and that would be 17,576,000. So Does that make sense, guys? That it's just 6 possible events, and we're just multiplying, we're using the multiplication rule 6 times, okay? Not meant to be difficult. Okay. If I was to ask you guys for the second one to where repetition is not allowed, okay, now be careful with this a little bit. So what would the first 3 be?
26, 25, 24.
Okay. And then what about the last 3? Would that be
10,
like
9.
8, 7, 9?
No, 10, 9, 8.
10, 9, 8, right? Because we started over with a new unique set, okay? So now we're going to get 10 times 9 times 8, okay? And that's just because we started over with a new domain, okay? We're not taking away any more letters. We're just taking away from the numbers again. Okay? So we're only going to get a slight difference between the first and second answer. So if somebody could just tell me what they got if they multiplied that out.
11,232,000.
All right, sounds good. So by slight, I mean a little bit more than 6 million license plates that we can't use, okay? So, but they used to be at least that you could allow to be reuse those. Okay. All right, so for the next one it says the first letter is a vowel and the last number is 0. We'll assume that repetition's allowed, okay? Unless I specifically say no repetition, you guys can use repetition with this, okay? So if the first one is a vowel, that means the first one has to be a 5, right? And then 26 and 26, because repetition is allowed.
10, 10, 1.
So then the next number could be whatever digit it wants, and then another 10, because the second one can be. And then how many different ways are there to pick a 0? 1, right? So you don't want to pick a 0 as the last digit, right? Because what happens if you put a 0?
Everything 0.
The whole thing becomes 0, right? And I often see that from students, so, but we don't want to do it. So there's only one way to pick a 0. You just pick the 0, okay? So, does that make sense, guys, as to why you don't want to put 0 down there, you just want to put 1 there? All right, and then we just multiply that out. So, was anyone able to figure out the product?
338,000.
All right. So, many, many fewer license plates than before. Okay. And you guys can see, like, just by changing 1 or 2 parameters, that this severely impacts the number of outcomes for this. Okay. All right. For the last one, first letter is a vowel, third is a consonant, and then the first number is 1. Okay. So, we have our 6 spaces. So if the first letter is a consonant, how many consonants are there?
21.
21.
First letter is a vowel.
Oh, it's a, wait,
Vowel.
first letter is a vowel, okay.
Yeah, the
So you
five.
answered my question correctly, I just asked the wrong thing. Okay. So the first is a vowel, so there's 5,
26.
26, and then there's 21, because I think the third was supposed to be a consonant, correct? And then if the first number is a 1, how many ways are there? Pick a 1.
One.
Just 1,
10.
and the other ones are just 10s, right guys? Okay. So this isn't meant to be difficult, right guys? Okay, you just go through, figure out the number of outcomes, multiply them together.
Easier than the set algebra.
What's that?
Easier than the set
Oh
algebra.
yeah, much easier than set algebra. Yeah, because it's just basic computation. And in most math classes, you've been doing basic computation all your lives. Did anybody get the product of this?
273,000.
Oh, 273,000, and then a bunch of zeros. Nothing extra. Thank you, ma'am. Easy enough, right guys? We wish the whole examination, that the next exam is going to be all in set theory, or I'm sorry, on counting methods thus far. Okay. All right guys. So, how many different hexadecimal numbers, and when we say, instead of numbers, we could say words if you would. So, let me scratch out the word numbers. And I'm going to put quotation marks. Let me put words. Begin with a number, end with a letter, and they're 4 characters long, with and without repetition. Okay, so let's just draw our... So we have 4 characters. Okay. So let's try to remember a little bit about hexadecimal. Okay, somebody tell me some of the stuff that comprises hexadecimal
A, B,
words.
C, D, E, F, right?
Okay, so there are
A, B, C, D, E, F. 6.
6 letters, right? So there are 6 letters. And then what else is there?
10 numbers.
10 digits, right?
Digits, yeah.
That's okay. So remember, it goes A through F and then 0 through 9. Okay, so that's where we have to fundamentally start, right, guys? If we don't know that, then we ain't getting anywhere with this. Okay. So, how many different hexadecimal words begin with a number? So that means there's going to be how many to start with? 10, because there's 10 digits. End with a letter.
So 6.
What's going to go in the middle then there, guys? 16, right? Because there's 16 total different characters to choose from. Okay. Does that make sense to everybody, guys? Okay, if we're using repetition, we just default back to the original number of outcomes that are possible. Okay. Then we just multiply this out. And if somebody can go through and tell me what the product is. 15,360. Lovely. All right. Easy enough, right, guys? Not meant to be tough. What about without repetition allowed? That's a little bit sneakier, okay? But we still have 4 characters.
The first one is 10.
The first one's got to be 10, right? So we pick the first one. It says it has to be a number, so there are 10 numbers.
Second,
Now, do we know what the next one is necessarily? Probably not.
the last one has to be 6, right?
We know that the, right, but the question is, we still have to think about what the last one is. So let's worry about the conditions that we know are absolutely certain, right? So what do we know about the last character? It has to be
6.
what? 6, right, guys? Okay, because there's only 6 numbers or 6 letters to pick from.
So the 9 and 8.
It's only 6 if a letter wasn't chosen.
Well, but we're not picking a letter, right? We don't, well, not yet, we don't have to. I'll show you why at the end, okay?
We're forcing us to end it with the letters, we have to.
Yeah, we're forcing
Right,
it.
or it could be number,
Right.
letter, letter,
Could be, yep.
which means.
So then, how many possible choices are there for this?
15.
14.
So,
And
Just
there's
the
13.
number and a letter.
Okay. Doesn't matter what order we pick it in, right, guys?
no, it
It's
shouldn't be.
multiplication. What do we know about
Should-
multiplication? It's commutative, it's associative, it doesn't matter what order we
Shouldn't that
pick
be
it
15 and 14?
in. No,
Because-
sir.
No.
No, we picked here and we picked here.
Oh, okay, okay, okay.
Right?
Sorry, yeah.
So because we've already picked 2, that
That's
means
14.
there's 14 and 13.
Yeah,
Okay? It doesn't matter what order they're selected in, because when we multiply it out, it's going to be the same value. Okay? So what I always try to tell students to do is pick the stuff that you absolutely know is certain, and then start to subtract them. Does that make sense, guys? Any questions? Okay. And then we just need a product for this. So 10,009. Okay. Any questions, guys, I can answer? Okay. And then we can do the same thing with these binary digits, okay? So how many binary numbers, and we could just say instead of numbers, begin with 2 zeros, end with 3 ones, 13 characters long, okay? And A with repetition allowed, okay? So we'll draw our 13.
That's a lot.
It is, but you know what? If you die from writer's cramp, let me know. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's not difficult. So it says that we begin with 2 zeros. Okay? So what should the first 2 entries be?
0, 0.
Nope, not
No,
0.
no, sorry.
1 and 1, right? Because there's in binary, what is there? There's a 0 and a 1, right? So there's only one way to pick 2 zeros at the beginning. Okay? So remember, let's just make a note here that for binary, the only outcomes are 0 and 1. It says it ends with 3 ones. So what should the last 3 entries be?
1, 1, 1.
1, 1, 1. Then what about all the stuff in the middle then? Just a
2.
bunch of 2's, right, guys? Because there's only 2 possible outcomes for binary. So it would be 1, 2, 3, 4, 5, 6, 7, 8. So essentially, guys, doesn't that work out to be 2 to the 8th? And 2 to the 8th is going to be 256? Yeah, maybe. So we go, I guess, 2, 4, 8, 16, 32, 64, 128, 256. Yep.
So, and it's 2 just because that's definition.
Oh, binary, right.
That's really why.
Yeah, binary only has 1s and 0s. There's only 2 outcomes. Okay?
Right.
Hence the prefix binary, so 2.
Right, yeah, no, I got like the 0 and 1.
Oh, that's okay.
what you're doing, but it's just,
Where the 2's are, you could pick a 0 or a 1.
Right, because it says it begins with 2 zeros,
Yeah.
so that's your 1s.
Yep.
Ends with 3 1s, so that's that. but it doesn't say anything else about the middle. Middle can be whatever it wants. So it could be a 1 or 0. 2 choices.
Right, too. Because
Because it could be either a 1 or a 0.
You're filling in how many choices you have.
Oh,
Yeah,
okay.
You have a choice.
there's 2 choices. It's either a 1 or a 0. Does that make sense?
Oh, right, got it. Yeah.
Okay? Yeah, there's no 2's in binary, but there are 2 choices. Okay? We're not trying to make a binary number out of this. We're trying to figure out how many binary numbers there are. Okay? And then probably the easiest question is B. How many different binary numbers begin with 2 zeros and with 3 ones without repetition? No, it's impossible, right? You can't. You have to have repetition, right? So that would be none.
Are we supposed to show all of that?
No, you could just say not possible. Actually, the correct answer would be 0, wouldn't it, guys? Because it says how many of them are there. All right. Does this make sense, guys? That's what our multiplication rule is. Okay, it's not difficult. It just is what it is. All right. So the last thing I wanted to talk about today was I wanted to talk a little bit about combinations and permutations and use of those. A lot of people think that they're the same thing, but they're completely not. Okay. In fact, in general, most applications use combinations. Okay. While fewer applications, but some do use permutations. Okay. The difference is a permutation order is important in which things are selected. Okay. So let me give you guys an example of a permutation. Okay. Let's say I start up here with Adam, and I give Adam $500, okay? And then Angelique gets $490, and then Paul gets $480. So each time I go through a person, I'm going to give them $10 less. Does it matter what order you are in the class?
No.
Absolutely. That is a permutation. The order in which you are seated or you are arranged matters, okay? That's a permutation. Okay? Any of you guys have ever played the lottery? Is the lottery a permutation? Yeah, because what happens is you get more money if you actually pick the right order, okay? Now, what if I said this? I'm going to start with Adam. I'm going to give Adam 500, Angelique 500, Paul 500, John 500. Does it matter when you get what seat you're in?
No.
That's a combination. A combination is when the order is not important, okay? There's sometimes, like for instance, I'm trying to think, with the lottery, that as long as you pick the numbers and they get picked, that's fine. But sometimes the order in which they're picked, okay? How many of you guys have ever done horse racing before? Okay, well you guys are all humane. I do the electronic horse, oh you did?
Like, really young.
Oh, okay, so you didn't know any better that the horses were being beaten, malnourished and all that stuff. That's okay, we eat them when we go to McDonald's anyway. I know, true stories. Regardless though, there are some times when it's a combination to where you just pick the first 3, okay? And then when you pick that's something called a trifecta, and there's something called an exacta to where you pick them in the exact order in which they come in. That's a permutation. So a trifecta is a combination, an exact is a permutation, okay? So I'm just trying to give you guys some real life examples as to the difference as to where combinations and permutations occur.
And it's all gambling.
No, you're absolutely right. Probability and statistics is heavy in gambling and that sort of thing, okay? And you guys are probably, like, how many of you guys have ever watched on TV, like at 3 in the morning, they have the poker tournaments on there?
Oh, yeah.
And sometimes you hear, oh, this guy has a doctorate in mathematics. And you're thinking, why is that guy doing poker? Well, guess what poker is?
Yeah.
Permutations and combinations. That's all poker is. It's just random probability of things occurring based upon what you think the other person might have. That's all it is. So if you know your combinations and permutations really well, you have a good chance of beating somebody else. Because remember, you're only playing against another person when you're playing poker, okay? That's why some of these people that go to like poker tournaments, they have no idea what they're doing. They just really quickly lose money because they're not betting against the probabilities. They're just betting on what they feel, okay? And it's great to feel something, but it's even better to know what you're betting for. So anyway, so let's go ahead and talk about like maybe some of the formulas that are arranged with these, okay? So like we said, permutation, the order is important, combination order is not important, okay? These are the formulas for being able to utilize permutations and combinations, okay? So the number of permutations, if I have n elements and I select r of those, okay, would be this formula right here, n factorial over n minus r factorial. So let's say for some reason, okay, I had 4 elements and I wanted to pick 2. Then n would be 4 and r would be 2. That's how many permutations I could get out of that. The number of combinations, so whenever we see this format, this is combination, And the only difference in the formulas is that there's an r factorial in the denominator. Okay? All right, so I want to show you guys some applications of combinations and permutations. Okay, again, these are fairly easy. They're a little bit more tedious than the previous, but they're not that difficult. Okay, so let's say for some reason we're considering the word ownership. Okay, I want to answer the following. Okay, so how many ways can the word be arranged to create new words? And when I say words, I just mean arrangements. It doesn't actually have to mean anything. Okay? How many ways can the word be arranged to create new words if the first letter must be E and the last must be R? How many letters must, or how many 5-letter words can be created from ownership? How many 6-letter words can be created if the first letter must be F? Okay, there's actually 2 different ways to do these problems. So I'm going to show you guys both ways to try to tackle these. Before I answer any questions for you guys about this, let me ask you guys a question, okay? What do you guys think? Is this a combination or a permutation problem?
This is the combination.
This is a permutation problem. How many letters are repeated in the word ownership?
None.
None. They are all unique and distinct letters. That means the order is important for every single letter, right? Okay. So this is a permutation because they're all unique letters. Okay, no repetition, right guys? So anytime you guys have elements that are completely unique, that's generally a permutation as to how we arrange it. Does that make sense, guys? We're going to see examples later where there is repetition and we can use a combination.
So you're saying the word ownership is a permutation, but when we do say the letter A there, then the order doesn't matter.
Oh no, it does. Like if I flip the O and the W around, I get a new unique word out of that, right?
Oh, each answer is
Correct.
going to be a permutation.
Right. Each answer itself is a permutation, right? Because they're all going to be unique. There's no repetition. You're never going to get a repeated word if you flip any of the letters around, right guys? So that's a permutation. So my first question is, how many ways can the word be arranged to create new words? There's a few ways you could do this, okay? One of which is, since there are how many letters? 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. Couldn't we do this? 5, 6, 7, 8, 9. Okay. How many ways are there to pick the first letter? 9. Second? 8. Third? 6, 5, 4, 3, 2, 1. That's one way to set up this problem. Or in other words, what's that the same as, guys?
Factorial.
9 factorial. By the way, in your calculator, you guys may or may not know, but there are some functions to help with factorials and combinations and permutations. Let me bring that up so that way everyone knows how to do that. In your calculator, you can just do 9, math, and then you go over to num, I'm sorry, you go over to prob. And then the factorial button is the 4th one down. Okay, so that's one way to do this. And then you get this horrible number of 362880. What's another way that we could do the exact same problem, maybe using a permutation instead? Well, permutation. How many letters do we have?
9.
How many are we selecting?
1.
Nope.
9.
All 9, right? We're trying to create all new words from that. Let's see if this gives us the exact same thing if we were to substitute it back in. Okay, so let me show you guys how to use the calculator to evaluate a permutation. Okay, you would type in the first number, which is 9 in this case. You would hit the math button, and you would go over to prob, and then you would go down to NPR, hit enter, and then 9 again. Okay, I'll do that again so that way you guys can see everything. And even though it might be difficult to see, you guys can see that we do get the same exact number. Okay? So I don't care which way you guys do it, okay, but make sure you know one of the 2 ways. Okay? So just in case you didn't see that, by the way, we're going to be doing this a lot with bigger numbers, so it might be good to make sure you know how to do it. You type in the first number.
That wouldn't work with if you had 2 different numbers.
That's correct. We'd have or 2 of the same.
No, I mean if if N and R were the same. No,
Oh no, it would still work.
I mean, I'm talking about in that little function where you're only entering 9.
Oh, you mean 9 factorial? Or
No, the second one you put.
Yep.
You only entered 9 one time,
I did 9, 9, yeah.
but you did 9 and 9.
Yeah.
Okay.
You do 9 and.
I didn't see you enter it twice.
Okay, yeah, let me show you 2 again. Okay, so 9, math, go all the way over to prob,
Ah, okay, I see. now.
select NPR, hit enter,
So
and
the
then
first
type in
number,
9 again. Right,
first number you're entering
Is
is
the
the
N.
N, and then you
Correct.
enter the R.
right. So basically it's N permutation R in the calculator. Okay, does that make more sense now, guys? Okay, either way you guys want to do it, I don't care. That's how it operates. Okay. So for the second question we have here, how many ways can the word be arranged, create new words, if the first letter must be E and the last letter must be R? Okay, so we still have 9 letters that we're working with, right guys? 5, 6, 7, 8, 9. How many ways do we pick the first letter? One, because it says it has to be an E. What about the last letter?
Same.
One as
One.
well. Remember the trick, guys? You fill in what you know first, and then you fill in the rest. And what's going to be in the middle, guys?
7, 6.
7, 6, 5, 4, 3, 2, 1. Or, in other words, that's going to be 7 factorial, right? 7 fact is 50, 40. Is that correct?
Yes.
Thank you. What if we wanted to use permutations? What's a way that we might set it up just utilizing permutations? P what?
9 and 2.
Not 9 and 2, unfortunately. Good try.
7
and
and
7, right? Because we have 7, with the 2 are fixed, right? We throw them away. As soon as we know that we picked the E, we picked the R, they're out of the equations. They're already done for us. So we have 7 letters that we're picking from, and we want all 7 of them, okay? In your guys' calculator, I bet you if you type permutation 7, 7, you're going to get 50, 40 as well.
Why is it 7, 7 again? Can you
Okay.
explain it again? I'm just,
Notice what we said, but we have to pick E and we have to pick R, right? Those 2 letters go away completely.
Right.
9 minus 2 is 7.
okay,
So now we have 7 letters and we want all 7 of them. That's how we get 7, 7.
okay.
Okay.
I'm just trying to picture what the N and the R, what they both represent, that's just,
N is going to be the total number we're picking, so that means we only have 7.
right,
And R is how many we're actually picking out of those 7.
okay.
Okay? In this case, we need all 7 letters. Okay? We didn't say that we're only picking 5 or something like that. Okay? Other questions, guys? Okay. For the third one, how many different 5-letter words can be created from ownership? Okay, so once again, we could do the space method. So 1, 2, 3, 4, 5. If you guys were doing the space method, what would you guys fill in there?
9 on all.
9, 6, 8, 7.
Or would you didn't say, oh, you're saying that no repetition. Earlier you stated you didn't say that.
Well, no, but because these are words and you only can pick from ownership, right? We're rearranging those letters. Okay, so consider how many different 5-letter words can be created, assuming no repetition, if we're just picking those letters from that, okay? If we were picking, if it was repetition, it would just be 99999, okay? Does that make sense, guys, when we're doing this? Like if we're picking from a word, once you pick the letter, it's completely done. You can't repick it, okay? What's another way if you guys were using permutations? How could you set that up?
So that's 9.
9, 5. Good.
9, 5.
So there's 9 letters that we start with. We are picking 5 of those letters. Right, guys? It doesn't matter which way you guys put this in your calculator. I'll just do the permutation method, and then somebody can verify this maybe. So we would do 9, math, probability, permutation 5. And I got 15120. Did anybody do 98765 or 96785? Or maybe nobody did anything with
Yeah, I
that.
did.
Okay.
15,
15120.
Yeah.
Okay. Nice. Either way we do it. And like I said, guys, I don't care which way you guys do it. I just want to make sure that you know one of 2 different ways to be able to arrive at the answer. Okay. And then for the last one that we had, it says how many 6-letter words can be created if the first letter must be an O. Okay? So we pick the O, we throw it away. There's nothing we do with that O. Okay? We have 6 letters. If the first letter is an O, that means there's 1 there. So then what would the rest of that be if we were using like the fill in the blank method?
8, 7, 6, 5.
Yeah, 8, 7, 6, 5, 4. Now, if I was to ask you guys to set up a permutation method for that, excuse me, what would the permutation that you guys think be for this one?
6, 9.
Not 6, 9, good try. 8, 5, right guys? We took one of the letters, we threw it away already, the O is
You
gone.
need to throw the slot away.
Right, and you throw the slot away as well, right? Because that letter is fixed and it's pinned, okay? So, this would say that there are 8 letters we're picking from, and of those 8, we only need 5 the slots, because the first slot's been picked, okay? Remember the other one that we did up here? We had 7, 7. We picked 2 of them, so those 2 are gone, and there's only 7 letters left to pick from for 7 spaces. Okay. Does that make sense to everybody, guys? Any questions about that? You guys could easily go in your calculator and figure that out. Did anybody do that already? And if so, would they get? 6720. Thank you, thank you. Okay. So everybody feel comfortable saying I can at least do it one of the 2 ways. I can either use the fill in the blank method or I can use the permutation method. Okay? Generally, what's going to happen is if these letters start getting much longer, the fill in the blank method becomes much more tedious, right guys? The permutation method is the way you want to go. But for right now, since we're only dealing with 9 letters, then we're okay. We'll see later that we don't want to do that forever. All right. So, one of the last problems I want to work on today is one of the classic jury problems. Okay. So yeah, everybody's favorite problem. I'm just taking a look at what we still have here. So suppose for some reason we have a jury and we're picking from a pool of 8 men and 9 women. Okay. So several different questions I want to ask you guys. Okay. Some of which we'll get to today, some of which we won't. Okay. How many 5-man juries can we create? How many 5-women juries can we create? How many 9-person juries can we create? 4 men and 5 women. Okay, so let's just do those first 3 today, and then Monday next week what we'll do is we'll do the other 3. Okay, so let me ask you guys first, before we even try to tackle this problem, okay? What do you guys think? Is this a combination or a permutation problem? This is a combination problem. How come?
Because it doesn't matter.
Yeah. They're basically indistinguishable, right? It just says women, okay? It doesn't give them names, it doesn't give them faces or anything like that. It just says men and women, okay? So if you can't distinguish between one element to the next, that's going to be a combination. If you can distinguish, that's a permutation, okay?
Even though you can distinguish between men and women, you're saying there's not an individual.
Correct, right. You can group the men and women, and we will see that that does come into play when we start throwing person juries together, okay? But for right now, it just doesn't matter. Okay, so for letter A, now this is where the space method doesn't work anymore, okay? So, it says how many 5-man juries can we create, okay? How many men do we have total?
9.
8.
8, sorry.
And we want 5 of those, right? So the way this would work is that we have 8 combination 5, okay? And again, that's just because we can't tell the difference from one man to the next man to the next man, okay? This is where we want to use our calculator. In fact, we have to use our calculator to make this convenient, okay? So, to be able to put this in your calculator, you use the exact same method, except instead of NPR, you use NCR. So 8, math, probability, NCR, and then this time instead of anything else, I'm going to put 5 in there. I got 56. Hopefully somebody else got the same thing. Okay, good. So this just is equal to 56.
And this is that formula where you end up with 8 factorial over 5 factorial times 8 minus.
Correct, right. If you wanted to do this by hand, because you have nothing better to do with your life.
So
You
you
would
can
set-
understand how.
No, that's okay. I understand.
Oh. Okay.
Yeah, if you wanted to do it like this, that's fine too, okay? I don't have any problem with you guys doing it by hand if you want to use the formula, okay? I'm just guessing that it just becomes tedious and inconvenient at some point to keep using this, especially since 8 factorial just starts to become a mammoth number that we don't want to deal
No,
with.
but you can trunk it after 5 once it comes to 5.
Yeah, I mean, you could simplify it that way if you wanted to, but still, it's just more
Just
convenient.
writing the formula down, not actually figuring it, and then plugging it.
Oh yeah, sure. Oh, I see what you mean. Yeah, this is actually what the calculator does. It just spits out that computation from that. Okay? All right, other questions, guys? Okay.
So how do you find N and R?
Oh, okay. So in this case, it says that there are, So we had 8 men that we're selecting from, right? So that's A. There are 5 man juries, so that would be R. Okay, so it's just given to us right away. Okay, does that make sense, John?
Yeah. I mean, I guess the R would.
Well,
Maybe this problem is specifically, I don't know where it's.
well, it's basically saying that we have a bunch of people to pick from, and we just want to make some juries out of it. So R is the number that we're selecting. So we're selecting 5 man juries. So that would just be the number that we're selecting. Okay, does that make sense?
Yeah.
Okay, so for letter B, it says how many 5 women juries can be created. Okay, so how many women do we have?
9.
9. How many do we want? 5. And then we would just go right in our calculator and we would do the exact same thing, except this time we used 9 instead of 8. Okay? If we wanted to, we could set it up using the formula. Okay, it doesn't matter which way we do it. 126. Thank you, sir. Okay, so that's easy, right, guys? Again, we wish the entire next exam was comprised of these types of questions. Now for letter C, this was a little bit different because now it says how many 9-person juries, so now we're not relegated to just men or women, that can be chosen that must consist of 4 men and 5 women. Okay, so let's just think of it as men and let's think of it as women. So we have our men and we have our women. Okay? We already said that we have a total of 8 men, correct?
Mm-hmm.
How many of those 8 men do we want for this problem?
4.
So 8, choose 4. Okay. The women, we already said that there are 9 women. In this problem, how many women do we want? 5. Okay. Now my question to you guys is, we can go in our calculators and figure these out, right guys? 9, 5 we already know is 126. And then 8, 4, if somebody can go in their calculator and tell me, was it? 70, thanks Greg. Sorry about that. So these are just from the calculator. But my question to you guys is, what do we do with those 2 numbers?
Multiply.
We're going to multiply them, right guys? How come? Multiplication rule, right?
Mm-hmm.
If event A has M outcomes and event B has N outcomes, then the total number of events is the product of those. Okay? Does that make sense as to why we multiply them? It's not addition. Now we are going to use addition later on Monday, okay? But for right now, we're just going to worry about being able to do this. Okay? And then if somebody can tell me what the product of this is going to work out to be, please.
8,120.
8820. Okay. All right. So, questions I can answer for you guys about being able to work with the combinations, okay? And again, the difference between permutation and combination. Permutation is going to be when the objects are distinguishable, combination or when they're undistinguishable. Okay, so no questions, guys?
You just can't use the space method at all.
On this one, no. You don't want to use it. I mean, you can try, but it's not going to work. So let's just say no, okay? Because it's a combination. Okay. Other questions, guys? Okay. So I have your guys' assignments. Let me give those back. And then once you guys get your assignments, you're welcome to leave. And then if you guys have some questions for me, I will answer said questions. Mr. Weber. Nice. Amazing.